Let us begin our discussion of numerical integration with a fairly well-behaved function. That way, we can make meaningful comparisons to known answers. I have chosen a sine function for our lesson today. Remember that integration represents the area beneath a curve. So if I integrate sine x from 0 to 6, that is represented by the regions in red. Conventionally, anything below the x-axis is negative area, so we subtract it from any area above the x-axis. We ignore the region in green because that is beyond my right endpoint of x equals 6. This is just a quick refresher on integration. In this case, sine x is easy to integrate. The exact answer, accurate to 9 decimal places, is shown in the very last line. We will retrieve this same number later in the lesson, so don't forget where it comes from. We don't always get functions that are easy to integrate. In fact, some functions are impossible to integrate exactly. In such cases, we must resort to other methods. We are about to explore some of those. Consider the picture here. We can evaluate the function at discrete points, y1 through y6, and then draw a rectangle to touch it in the right corner. Each rectangle, A, B, C, D, E, and F, has a different area, but we can add them up to estimate the total area. This is called Riemann Summation. Notice the width of each rectangle is h. In this case, h equals 1. As just mentioned, we can estimate the total area by adding up the area of each rectangle, A, B, C, D, E, and F. These are sometimes called panels. Remember that each rectangle has a width of h. This is important because once again our numerical method depends on even spacing from one data point to another. That h can be factored out. In the last line, I have represented the expression for area using sigma notation. Basically, we add up all the y values from y1 to y6 and multiply that sum by h. H is sometimes called the mesh size. It's just the spacing between neighboring x values. This is what that calculation looks like from a data table. We add every number in the red box and multiply by 1, our mesh size. The final answer is boxed in green. That number is our estimate for total area using 6 panels. You may have thought that was a rather crude estimation of area because the rectangles tend to overshoot the function on the uphill side and undershoot the area on the downhill side. So what if we double the number of panels to 12? This is the same as saying we cut our mesh size in half, from 1 to 0.5. The formula looks virtually identical for 12 panels as it does for 6. We just have a few more numbers to add. We can double the number of panels yet again. Just imagine that if we did this enough times, the estimation for total area will get closer and closer to the true value. We are just adding more and more y values each time and multiplying by a smaller and smaller mesh size. Obviously, this approach has its limitations, but it's a good place to start from a conceptual standpoint. This table summarizes the total area for 3 different mesh sizes. The error column is the true value minus our approximation. That process can be seen in color coordination here. Whereas I've only shown this for the first row, the same rule applies to the second and third row as well. What if we run through the same process again, except this time we draw rectangles to touch at the left corner instead of the right? It turns out that we get very similar results, but some of the details differ. Adding up the area of each panel will give us an estimate of the total area. Again, the width of each panel is h, which can be factored out, so we are still adding a bunch of y's and multiplying the sum by the mesh size. Notice we add y0 through y5, so we leave off the rightmost value, y6. Last time we added everything except the leftmost value, y0, so that's an important distinction. Here is the calculation from a data table. We add every term in the red box and multiply by 1. Notice we did not add y6. The final answer is boxed in green. That number is our estimate for area using 6 panels. Again, we can get a better estimate for total area by increasing the number of panels. Like before, I've cut the mesh size in half. This is the calculation for that. As shown in the red box, we add every term except y12. Then we multiply by 0.5, the mesh size. The final answer is boxed in green. We can double the number of panels once more to get an even better approximation. That is represented visually in this picture. The data for 3 different mesh sizes is summarized in this table. Once again, the error is calculated as the difference between the exact value from our actual integral and our area approximation from the summation. Now let's take a look at the error for the right and left method. Notice that if we decrease the mesh size by a factor of 2, the error is also reduced by a factor of approximately 2. I have shown the calculations to the side. Harkening back to big O notation, this pattern implies that our method of taking Riemann sums is of order h. For a numerical method, that's not very good if you want to make an accurate estimate of the area. Obviously, we can see that even a mesh size of 0.25 doesn't give us a very good estimate of the integral. Now you may have noticed the table on top tends to underestimate the true value. Meanwhile, the table on the bottom tends to overestimate the true value. And the error for a given mesh size is comparable. So do you think we could get a better estimate of the integral by averaging the right and left method? The answer to that question is yes. Geometrically, this amounts to representing each panel by a trapezoid instead of a rectangle. With only 6 panels, we can see that this is already a much closer estimate than Riemann sums gave us. It is the same idea of adding individual panels to estimate the total area. The big difference here is in the formula for area. For a rectangle, it is simply base times height, h times y. For a trapezoid, we have to find the average y value for each panel and multiply by the width h. This h will factor out. However, notice a couple differences between the trapezoid summation and Riemann summation. We now include every y value, including both y0 and y6. Every other term between them is multiplied by 2. The last line represents summation as sigma notation. The calculation for that is shown here. Mesh size, in orange, for 6 panels is 1. The leftmost and rightmost y values are green. Every term in the red box is multiplied by 2. For calculation in a spreadsheet, I have simply added 2 more columns. Each term in the 5th column is the product of y sub j and the weight. So the same answer can be obtained by adding every term in the blue box. This habit will prove useful when we learn Simpson's rule. As we did with Riemann sums, let us cut the mesh size in half. Now we have 12 panels, which is twice as many as we had before. The top line shows the sigma notation for 6 panels. It looks very similar for 12 panels, as seen in the second line. The last line shows sigma notation for an arbitrary number of panels, n. The calculation for 12 panels is very similar as before. We just have a few more rows in our data table this time around. Once again, the leftmost and rightmost y values are boxed in green. Every y value in the red box is multiplied by 2. Those values can be added up, as seen in the blue box, and then they're multiplied by the mesh size h, shown in orange. We could repeat the process for 24 panels, and so on and so forth. This table summarizes the approximation for 3 different mesh sizes. Notice already that for any given h, the area approximation is much closer to the definite integral than the Riemann summation using rectangles. As before, the error is simply the difference between the definite integral and the trapezoid summation. Let's take a look at this now. If I reduce the mesh size by a factor of 2, the error decreases by a factor of 4. Similarly, if I reduce the mesh size by a factor of 4, the error decreases by a factor of 16. Since 4 squared is 16 and 2 squared is 4, this leads me to suspect that the trapezoid method is of order h squared. That is why it outperforms rectangular summation, which is only of order h. Stay tuned for the next few lessons. Today we saw a geometric approach to developing the trapezoid rule. This is useful for an intuitive understanding, but it has its limitations. Next, we will see how the trapezoid rule is yet another numerical method that results from a Taylor series expansion. From that, we will see extensions to increase our order of accuracy beyond h squared. In the end, what all this means is that we are developing better and better methods to approximate the area under a curve. This can be incredibly useful, especially in cases where we cannot directly integrate a function. Can you think of other situations in which a numerical approach to integration could prove useful? Let us know in the comments section below. Thanks for watching. I will see you next time.